Physics Part 394. Let's talk about nuclear fission and nuclear fission. Nuclear fusion and nuclear fission. Well, the light nuclei between A and B on the graph may combine or fuse to form larger nuclei with larger binding energies per nucleon. This process is called nuclear fusion. For the process to take place, conditions of very high temperature and pressure are required, such as in stars like the Sun. Heavy nuclei between B and C on the graph, when bombarded with neutrons, may break into smaller nuclei, again with larger binding energies per nucleon values. This process is called nuclear fission. Well, the figure highlights nuclides which may undergo the fusion blue part of the curve or fission red part of the curve. In order to increase their binding energies per nucleon, when nuclear fission, when nuclear fusion or fission takes place, the nucleon number of the nuclei involved change. A higher binding energy per nucleon is achieved, and this is accompanied by a release of energy. This release of energy during fission reaction is how the present generation of nuclear power stations produce electricity. So we've got an example for you. The binding energy of helium-4 nucleus is 28.4 MeV. Calculate the binding energy per nucleon. The helium-4 nucleus has 4 nucleons. The binding energy per nucleon is thus 28.4 divided by 4 equals to 71 MeV. 7.1 MeV per nucleon. Now it's your turn. The binding energy of a carbon-14 nucleus is 102 MeV. Calculate the binding energy per nucleon. Nuclear fission. Within the nucleus of an atom, the nucleons experience both attractive and repulsive forces. The attractive force is called strong nuclear force. This acts like a nuclear glue to hold the nucleons together. The repulsive forces are the electric Coulomb's law forces between the positively charged protons. Gravitational forces of attraction exist, but are negligible in comparison to other forces. Stable nuclei have much larger attractive forces than repulsive forces. Stable nuclides generally have approximately same number of neutrons and protons in the nucleus. That is the neutron to proton ratio, which is close to 1. In heavy nuclei such as uranium and plutonium, there are far more neutrons than protons, giving a neutron to proton ratio of more than 1. For example, uranium-235 has 92 protons and 143 neutrons, giving a neutron to proton ratio 1.55. This leads to a much lower binding energy per nucleon compared with iron, and such nuclides are less stable. Any further increase in the number of neutrons in such nuclei is likely to cause the nucleus to undergo nuclear fission. Nuclear fission is the splitting of heavy nucleus into two lighter nuclei of approximately the same size, approximately the same mass to be exact. When a uranium 235 nucleus absorbs a neutron, it becomes unstable and splits into two lighter, more stable nuclei, the most likely nuclear reaction. This process is called induced nuclear fission because it is started by the capture of a neutron by a uranium nucleus. Each of the fission reactions described by this equation results in the release of three neutrons. Other possible fission reactions release two or three neutrons. If these neutrons are absorbed by other uranium 235 nuclei, these too may become unstable and undergo fission, thereby releasing even more neutrons. The reaction is described as being a chain reaction, accelerating chain chain reaction which is accelerating. This is illustrated in our figure. If this type of reaction continues uncontrolled, a great deal of energy is released in a short time and a nuclear explosion results. And countries have been using this fission process for nuclear explosions, nuclear bombardment, and for the use of atomic bomb. This is what we call the fission fragment accelerating chain reaction, the fission process. If the number of neutrons which takes if the number of neutrons which take part in the chain reaction is controlled so that the number of fissions per unit time is constant, rather than increasing the rate of the release of energy can be controlled. This situation is illustrated in the figure. These conditions apply in the reaction and modern nuclear power station, where some of the neutrons released fission reactions are absorbed by the control rods in order to limit the rate of the fission reactions. Nuclear fission reactor.